Testing, testing. This is check 1, 2, check 1, 2. Second recording. Okay, hopefully this works this time, all right? So, a little correction on the sheet here, even though it says Unit 3, Day 7. This is Unit 3, Day 5, okay? So, obviously this is the one from last year. Okay, I'm just tweaking my stuff here, okay? So, Unit 3, Day 5 deals with the discriminant, okay? So, we'll talk about what the discriminant deals with, but it deals specifically with roots, okay? And that's the only thing that we're going to be talking about today is roots and their behavior, right? Whether the roots are going to be, you know, a good number, right? A whole number or a rational number, okay? Or sometimes you get those nasty irrational numbers, right? 8.2357, 8.7, you know, something like that, okay? And then also there's cases where you just get one root, and then there's also cases where you get no roots, which means our quadratic is not crossing the x-axis, okay? So first let's talk about what the roots are. Again, it's just where they either touch or cross the x-axis. So here we have two roots, right? This one is just touching, okay, the x-axis, and then the one on the right here is obviously going all the way through, okay? But whether it touches it or crosses it, those count as a root, okay? So we have two roots here. Here we have four roots, okay? Here we have one root, okay? This is a linear equation, right, as you can see, okay? And then here we have two roots, and then here we have no roots, just like the song, okay? And so down here, there's going to be kind of like what the examples that we're going to see today. You're going to see two roots, you're going to see no roots, or you might see okay, where it touches the x-axis once. More importantly, it touches it at the vertex here. All right, and so this is one root. Okay, and so that's what the discriminant determines, whether or not we're getting two roots, no roots, or one root, and then also whether or not our roots are rational or irrational. Okay, so the definition of a discriminant determines the nature of the roots. Okay, and so we'll discuss what the nature, okay, quote-unquote nature of the roots means, okay? So first let's talk about what the discriminant looks like. Well, should look kind of familiar. B squared minus 4ac, okay? And this is something, this formula, or at least part of this formula, we have seen somewhere else, right? More importantly, it's this right here. X is equal to negative b plus or minus the square root b squared minus 4ac all over 2a. Okay, so here, if you look, examine it closely, you'll see our discriminant is underneath our radical. Okay, so a lot of this involves taking the square roots. Okay, what happens when you take the square root of a number that is a perfect square? What happens when you take the square root of a number that's not a perfect square? And what happens when you take the square root of a number that is negative? Okay, so that being said, all right, first we need to talk about what a rational number is. A rational number is any number that can be represented as a fraction. Whoops. That's two words. A fraction. Okay. All right. Also, it has repeating decimal or pattern. Okay. Or is also terminating, which means it doesn't go on forever. Okay, so some examples of that would be stuff like this. Okay, now any whole number, so if you take the number 2, right, well you can put that over 1. Okay, 2 over 1 is a rational number. Okay, also 2 over 3 is a rational number, right? That's 0.6666, 6 repeating. Okay. Another rational number would be 1 over 8, which is equal to 0.125. Again, it's terminating. Okay. And then lastly, you might see something like this, 125, 125, 125, okay, where that 125 is the repeating decimal. And so as long as you have a repeating pattern, that is also a rational number. Okay, so that's all the criteria for a rational number. And then the irrational number is just basically opposite all of that, right? Cannot be represented as a fraction. Okay, it's repeating, I'm sorry, non-repeating. And non-terminating. Decimal. Okay, so a perfect example would be pi, right? 3.14159265554, okay, so on and so forth as that continues on, okay. There's no pattern, and it goes on forever. So when you're thinking of irrational number, think of the number pi, right? We can't write that as a fraction. I mean, we could, I guess, but you got a non-repeating, non-terminating decimal at the end anyway. So irrational numbers look something like that, okay? So also, any irrational number, okay, any square root of something that's not a perfect square, so square root of 3, square root of 26, square root of 29, those are also all irrational numbers, okay? Because there's going to be no pattern, okay? It's going to have non-repeating, non-terminating decimals, okay? So that's a quick rundown on rational and irrational numbers. Now let's talk about the discriminant part, okay? So what that actually means. All right, now again, it just determines the nature of the roots, all right? So this b squared minus 4ac, remember this comes from our quadratic equation written in standard form, where a, b, and c are those two numbers that fall in front of the x, and then your c value is your constant at the end. Okay, so if this b squared minus 4ac is greater than 0 and is a perfect square, the type of roots are going to be real, they're going to be rational, and you're going to have two roots. Okay, so if you think about it, if that b squared minus 4ac is square root of 16, well, you're going to have plus or minus 4, right? You're going to have two different roots. Okay, now if this was like, I don't know, 3 over 2, right? Again, you would get a number that could be represented as a fraction, right? So, therefore, anytime you get a perfect square underneath that radical, okay, you're getting a rational number, and you're also getting two roots. And that means your graph is going to look something like this. Where it crosses the x-axis twice, and the numbers right here, your roots are going to be nice whole numbers, or at least some number that can be represented as a fraction, right? Like 3 over 2 or 5 over 7, stuff like that, okay? Now, the next one, okay, this b squared minus 4ac is not a perfect square, so if you're taking the square root of like 17 or square root of 22, okay, one of these numbers that isn't a perfect square, okay, what that means is you're still getting real roots, right? You're still getting a real number, but your roots are going to be irrational, and still you're going to get two roots, right? So you're going to get a number that's going to be like 8.2257, repeating with no pattern, okay? That would be an irrational number, okay? And then again, what it would look like is you'd get that intersection, okay? But your roots here, okay, are not going to be nice numbers, right? They're going to be irrational numbers, okay? All right. The last one, or last two, b squared minus 4ac, right? If this is all equal to 0, okay, that means you're getting real roots, okay? They're going to be rational, but you're only getting one root, okay? And they call that equal roots, okay? And think about it. What that means is this. If all this, so if we had x is equal to plus or minus, or let's see if we had x is equal to 3 plus or minus the square root of 0 over 2, right? Well, we would get x is equal to 3 plus square root of 0 over 2, and x is equal to 3 minus the square root of 0 over 2. Well, we're still just going to get x is equal to 3 halves, x is equal to 3 halves, right? And so our root, all right, we're still getting 2 roots, but they're actually the same, right? 3 halves is the same as 3 halves. So that's why they call them equal roots, because we're still technically getting 2 when we solve out our quadratic, but we're only getting 1 intersection, okay? And so it looks like this, okay, where the vertex is only touching it once. Okay, last but not least, all right, when this is less than 0, which means we're getting -1 or -3, okay, we are getting not real numbers, but imaginary roots, okay, which means our graph is not touching the x-axis at all. Okay? All right, so this discriminant, okay, determines not only whether it's going to be real or imaginary, but also how many roots you're getting and what those numbers can look like. So that's what I mean by the nature of the roots. Okay, let's head down here. All right, so the first one's asking, given the discriminant, okay, describe the roots and determine which have rational factors. Okay, so in all these, this is the number that appears underneath our radical. All right, so square root of 28, well, that's going to be a real number, but it's going to be irrational. All right, so rational factors, no. And how many roots are we going to get? 2 roots. Okay, how about here? All right, when our discriminant is negative, okay, well, we're going to get an imaginary, okay, and so rational factors, no, okay, and typically you still get 2 roots. Okay. When a discriminant is 100, well, 100 is a perfect square, so we're going to get real, we're going to get rational, and we're going to get 2. So rational factors, yes. Yes, we will. Yes, please. And lastly, when our discriminant is 0, okay, we're going to get real, we're going to get a rational number that's going to have 1 root. Okay, so rational factors, yes. Okay, so this last part, okay, we're going to use our discriminant in order to answer these questions here. So it says the roots of this equation are equal, all right, when k is equal to what? Okay, so equal means, remember, that's just a fancy way of saying, okay, when our discriminant is equal to 0, right? When we get equal roots, when we're getting only 1. Okay, so let's set that equation up. So my a value here is 1, my b value is k, and my c value is 16. So I just plug in what I have here, right? So b is just going to be k squared minus 4 times 1 times 16 is equal to 0. So I get k squared minus 64 is equal to 0. Okay, so we need to figure out, okay, which one of these numbers, okay, if I substitute it in for k, do I get a 0 for? All right, and basically we're looking for something squared equal to 64. That means it has to be 8, right? 6 squared is 36. 36 minus 64 is not 0. 16 squared minus 64 is not 0. And 16 minus 64 is not 0 either. Okay, so again, we're getting equal roots, right? Which means we're getting something like this. We're getting plus, so we're getting 6 plus or minus 0 over 5, right? So we'd get 6 plus square root of 0 over 5, 6 minus square root of 0 over 5, and so we're getting the same fraction for each, 6 over 5, okay? So that is what's happening, sorry, when you're getting equal roots. Okay, imaginary roots. Okay, this is when our discriminant is less than 0. Okay, so what does that look like? Well, let's fill in our A, B, and C values. So A is 2 here, B is 8, and C is just K. Okay, so let's fill in what we know. So we got 8 squared minus 4 times 2 times K is less than 0. Okay, so we're going to get 64 minus 8K is less than 0. Okay, so we need to figure out which number that I multiply by 8 will ensure that 64 minus that particular number will get us larger than 0. Okay, so, well, 8 times 4 is 32, so 64 minus 32 is not less than 0. All right, 64 minus 6 times 8. Well, 6 times 8 is 48, so 64 minus 48 is still less than 0. What about 8 here? Okay, well, plug in an 8 there. We get 64 minus 64, which is equal to 0. But the question isn't asking where it's equal to 0. It's asking for when it is less than 0. So our answer has to be 10. All right, it has to be 8 times 10, which is 80. So we get 64 minus 80. Whoops, I need to put that equal sign there. Which is going to give me negative 16, which is certainly less than 0. Okay? All right. Last one of this section. All right? We're looking for when the roots are real. All right? So we want our b squared minus 4ac greater than or equal to 0. Remember, if it's equal to 0, you're still getting a real root. Okay, so we want to be greater than or equal to. All right, so my a value is 3, b value is k, c value is 2. So I go k squared minus 4 times 3 times 2 greater than or equal to 0. K squared minus 24 is greater than or equal to 0. Okay, so we need to figure out which one of these numbers, okay, will still allow me to be greater than 0. Okay, so 4 squared is going to give me 16. 16 minus 24 is not greater than 0. How about negative 3? Well, negative 3 squared is 9. So 9 minus 24 is not greater than 0. So if 3 and 4 don't work, certainly 2 isn't going to work. So it has to be 5. And let's think about that. Negative 5 squared is equal to 25. Is 25 minus 24 greater than or equal to 0? Yes, it is. Okay. Number 5. Find 3 different values for c that make the following quadratic equation factorable. Okay. So, what we're looking for here is we're looking for what value of c will allow for us to factor this problem. What I mean by factor is that we're going to get x plus something, okay, in parentheses. All right, so we're looking for a nice value for c. Okay, so the first one I can think of is 2. So x plus 1, x plus 2, right? Add those two together. What's 2 plus 1? That is equal to 3. 2 times 1, that's equal to 2. Okay, so 2 is going to be one of our numbers. Okay, let's think of another one. Now, all I'm trying to do is get a positive 3 in there. So I'm going to go with plus 4 and a negative 1. Okay, so 4 plus 1, or minus 1, I'm sorry, is equal to 3. Okay, and then 4, whoops, times a negative 1, well, that's negative 4. So negative 4 would be another option. Let's keep going. Okay, so I'm just coming up with numbers that I can use to equal 3. All right, so how about plus 5 and then negative 2? Okay, all right, add those together. 5 minus 2, well, that gives me a 3. And then 5 times a negative 2, well, that'll give me a negative 10. So negative 10 would be another one. Okay, I'm going to do one more just so you guys figure out the pattern here. So I'm going to go plus 10 and minus 7. Okay, 10 minus 7, well, that's 3. 10 times a negative 7, that's negative 70. So negative 70 would be another option for C. Okay. Take a look at number 6. All right, the quadratic function h of x is graphed to the right. Okay, which of the following could be the discriminant of h of x? Okay, so let's take a look at our roots. Okay, we got nice numbers here. All right, so what that means, all right, is that our roots, okay, I'm sorry, not our roots, our discriminant is a perfect square. How do I know that? Because negative 9 and 0 are rational numbers. Okay? If we had irrational roots, then I would know that whatever our discriminant was is not a perfect square, because remember, this appears underneath our radical. Okay? So perfect square there will ensure that you get nice numbers. A non-perfect square will give you irrational numbers. Okay? So, that being said, which of the following could be the discriminant? Well, okay, we don't want 0, right? Because how many times we see it cross the x-axis? Twice. Okay, so 0, when our discriminant is 0, that means we're only getting one root. Okay, can't be this one either, because that means our discriminant is less than 0, which means we're getting imaginary. All right, take the square root of 10. Okay, well, we get irrational numbers. All right, so therefore it can't be 10 because we have rational roots, and so our discriminant has to be 16. Right, because when you take the square root of 16, we get plus or minus 4. Okay, which means whatever we're getting for a root here, we're getting rational numbers. All right, so remember, you take the square root of anything that's not a perfect square, you get irrational numbers, which means we would get an irrational root. All right, and lastly, number 7. Okay, use the discriminant to find all values of k so that the equation 2k squared plus 8x plus k has exactly one real solution. Okay, so being said, all right, my a value is 2, my b value is 8, and my c value is just k. Okay, so what we're looking for, all right, exactly one solution. So we want our discriminant to be equal to 0. Okay, so let's plug in the blanks here. 8 squared minus 4 times 2 times k equals 0. So I get 8 squared minus, oops, 8 squared is just 64. Hello, McFly. 64 minus 8k is equal to 0. Okay, so now we could solve, right? Subtract the 64 and divide by negative 8, okay? But we don't need to do that, okay? This is algebra 2, all right? We can use our intuition here. What number does k have to be in order to get a 0 here? Well, k would have to equal an 8, okay? So if k was 8, we would get 64 minus 64 is 0, which means our discriminant, okay, so again, I'm just making up numbers here. Right, maybe we had a 2 in the front here, and this is 4. So we would get a 0 here, right, for our discriminant. And so we would get 2 plus square root of 0 divided by 4, and 2 minus square root of 0 divided by 4. So that is why we're getting one equal root, because here we're getting 1/2, and here also we're getting 1/2. Okay? So that's what I mean by equal roots. All right, or one real solution. All right, so hopefully this video will take here. For homework, I want you guys to try the even problems. Now we'll go through the odd problems during class. Okay? So good luck, you guys. And I'll see you guys soon.